All right, next up is John Orlando, the CEO at Epic Solutions, located in Illinois. That was close. So he will be discussing a little bit about embedded and mobile as it relates to mobile.
Thank you, Ben. Everybody hear me okay? Yes, we're good? Awesome. All right, so yeah, this is actually our first year presenting at the GNU Radio conference. We've had folks from our company here in the past participating. Today, we'd like to talk to you a little bit more about what we're doing to take the radio and move it as close to the computing platform as possible. So we have this talk entitled Big Things in Small Packages. We'll be talking a little bit about some of our products that help kind of go this way, but other people's products as well to kind of push in this general direction. So let's get right to it. A little bit of background, my colleague Megan Zori, who actually supports a lot of the GNU Radio blocks for our radio platforms, had to leave last night, so she's not able to be here today. But she was a significant contributor to the work kind of going in we'll be talking about today. A little bit of background about us. As Ben introduced me, I started with two co-founders at Epic Solutions back in 2009. We're kind of in the space of making really small software-defined radios. I previous experience in the wireless telecom industry, very heavy on the cellular side, and we've been around about 5.5 years now, going on 6 years, and continuing to grow. We'll have another plug for we're hiring at the end as well, much like the other folks that are trying to hire people here. In my spare time, I'm kind of a big robot nerd, so if anybody has any insights into merging SDRs and robots, come talk to me. I would love to ask about that. Similarly, Megan, if you saw her yesterday, I know there were some folks here on Monday and Tuesday that saw her. We had a contingency of folks that were working with our platforms. You'll see her popping up on mailing lists from time to time, as well as our support forums if you're using our products. Okay, so some general observations here. These aren't going to be too shocking to anybody, but over the course of time, GNU Radio benefits from different things, right? It benefits from processing power getting bumped up, faster CPUs, faster hard drives, better RAM, more transistors getting packed into CPUs. All these things make GNU Radio better, right? It's not too shocking. But there's a lot more to the equation as far as what really ends up making GNU Radio work the best. There's interfaces you have to be able to get samples into and out of a computing platform. Things like USB 2.0 migrating to USB 3.0 and PCI Express really start to make a big dent in that, and GNU Radio ends up winning. And last but not least, a lot of talk about ArcNock and some of the other capabilities that are getting moved into the FPGA that ends up playing a really big place in this whole equation these days to take advantage of what is available there to further enhance GNU Radio. So digital world in general getting better and better and better, and people are doing more and more awesome things with GNU Radio. So there's this corollary piece on the radio side, right? The actual RF side itself is that where 20 years ago radios were ginormous, they keep on doing this shrinking thing. So it's not Moore's Law, it's these other crazy advancements that are getting brought to market where RFICs are getting more integrated, which helps mush the space, the physical requirements down. People are getting more advanced capabilities in smaller process nodes as well, so you end up getting very small chips that can do lots of interesting things. Back in 2008, when Analog Devices first introduced the ADF4350, which is near and dear to my heart, it was actually one of the main chips that kind of kicked off some of our early platforms right when we started Epic. It was a big transformative step that has continued to percolate in lots of different platforms. It was used in some of the Edge boards. We've seen it in some of the other platforms that are out there as well. So kind of a big jump in being able to build very small, low-power, configurable LOs, a big piece of the equation. A little bit further past that, a company Live Microsystems out of the UK came onto the space with one of the first RFICs that was publicly available. It really had a kind of antenna to digital bit solution in a single chip. And it was pretty cool, right? It did things that not a lot of people had access to at that time. Technology pushes on, a few years past, Analog Devices came out with their 9361 and 9364. Even further improvement on capability, and believe you me, there is no shortage of people trying to push that space further and harder as possible. And all these things come together, and GNU Radio ends up winning. So we got this bump up in the computational side and this corresponding bump up in the RF side. So let's kind of consider this case of we really are interested in seeing what we can do to blur the lines between the host computing platform and the radio, right? So right now, a lot of times it's you're plugging in cable, you're running power over your radio, you have some other configuration. Well, when we want to start thinking about what you want to do to remove those limitations, you start getting a whole other world of questions that pop up. Well, what does that really mean? What other problems do you get introduced? How small do you have to be able to really do an interesting integration? And eventually, in the long run, if we really have all these fantastic little tablets and computing solutions that are wonder devices in our pocket, my assumption is there will just be a flexible radio in there that eventually will be able to support these sorts of applications. So we do a lot of thinking about this. You'll see a little bit sort of in the next couple slides of the various products that are out there that they contribute in different ways to the solution space. And ultimately, what does this mean for computing radio? Because at the end of the day, that still seems to be one of the predominant frameworks that people are able to take advantage of to make these systems turn into real-world things. Where spectrum plots are interesting. I think we all have a warm place in our heart for spectrum plots, but at the end of the day, we need to be able to do something with that data. And the more we can do with it, the more interesting and the faster we can kind of push down some of these places. So we have to start the question then, when we start talking about merging and small, saying where do we want to run GNU radio? And everybody's favorite answer to this is, of course, everywhere. But let's try to put a little bit more context behind what that really means. So most people that are probably running GNU radio in the audience today are running it on their desktop at work, or maybe they've got a lot of laptops here, people are doing their laptop run. We're interested in starting to push more, and have been pushing more into smaller and smaller devices, as well as moving into the portable computing space on the tablet side, as well as things where you're looking at just small single-board computers. So I won't whip out a laptop here and show you, but things like where you have small integrated computer modules that are commercially available today. They have a lot of the interesting, how do you get a hard drive and memory and CPU in a relatively small package. And in this case, it's actually passively cooled. This is a quad-core x86 with lots of I/O all around it, but just a standard computing module that you can go buy commercially off the shelf. There are lots of other folks that make single-board computers where you can, this is a Jetson board with an NVIDIA Tegra CPU plus GPU, if you're familiar with them. So lots of these computer boards keep percolating onto the market, and they become very interesting places to be able to run GNU radio if you can figure out how to get the radio itself, the actual RF stuff, properly integrated into it. So that's kind of where we have spent a good bit of time thinking about these problems. When we go to actually move the radio in, the questions that start to pop up that we have to deal with, and I apologize for the smallish font. There's only a couple places where the font drops down. You want to have very intimate contact, very intimate electrical and mechanical interfacing between the radio itself and the host computing platform. Few cables as possible to make things easier, and if you can get that, that helps the overall how do we make it mobile. The tighter coupling actually has its own set of problems associated with it. You have to deal with interference. You start talking about places where you're putting RF and digital really, really damn close to each other, and all kinds of wacky things can happen if you're not thinking about it. So things that have to be considered. The throughput between the CPU and the radio also starts to make a really big difference. I mentioned before USB and PCIe are kind of the two prevailing solutions that a lot of people are going with these days. But in general, you want to be looking at how do I minimize the number of CPU cycles required to get those samples into those CPU and do something interesting with them, right? Power also starts to be an interesting piece of the equation. We're talking about mobile use cases. The last thing I want to have to do is plug it into a wall to have my system run. So we're talking about running with a battery, or we're talking about having some other solution where you can, at a reasonable power consumption, be able to be detached and actually run the radio platform on the whole. And last but not least, antenna integration is always a challenge. You see all the tables, and as you're looking around today, you see little various whip antennas kind of sticking up, and people are doing, feverishly doing the various experiments with them. It's an appendage to the SDR problem that you have to deal with, and the more that we can move in the direction of having to not worry about that, the better. Physics is still hard, and we'll talk a little bit about that. as we go here. So yeah, so some of the example solution spaces that are out there, I've seen dozens of B210s here in the last couple of days, right? A relatively small platform that has a lot of what we just talked about, right? It's got fast transport, it's got USB 3, reasonably portable. You can bus power it if you're using the 1x1 mode, so it kind of falls in some of these proper niches of how do I go mobile. I saw Tom Rondeau with a couple of B200s or 210s plugged into his laptop, kind of cooking away over there. So falls interestingly in that space. And there's various people playing with the different dongle classes that are out there. The RTL SDR dongle is near and dear to everybody's heart. The FunCube dongle, which I've always been a fan of personally, just as an interesting little semi-custom solution for being able to kind of go relatively portable, right? You plug it in your laptop and you're on your way. You don't need to worry about power. It's got an antenna port right there. It's very small. The bottom image there is one that we've spent a bunch of time working on, which is called Sidekick. So Sidekick is a mini PCI Express card. If you're not familiar with mini PCI Express, it's a standard that's been around for quite some time. If you pop open the back of your laptop, the odds that you will have a mini PCI Express slot is relatively high. Usually they're relegated for Wi-Fi cards or for cell modem cards if you want to plug in. So about a couple of years ago, we started thinking, well, that is a really interesting place to start thinking about trying to put a radio, right? It solves a lot of those key pieces that we were interested in. It's got power in the slot. It's got very tight integration with the host system itself because you've got PCI Express and USB sitting there. In a number of cases, you've got antennas already pre-wired into the computing device because it was meant to either be Wi-Fi or to be a cellular modem card. So it kind of got us kind of kicking down the path of this is interesting to us. This seems like this helps push in this general direction. And the actual number of host platforms that it starts to open up for us becomes relatively large very quickly. So you have the desktop space, of course, where you can you're hard-pressed to find a motherboard these days that doesn't have some form of PCI Express where you can take an adapter board and go mini PCIe to PCI Express. It kind of goes down from there, though, when you move into laptops. I mentioned before that you can easily plug in this to the back of the laptop. If you don't have a laptop with a mini PCI Express card inside, but you do have an Express card adapter, which was another form factor that's been around for quite a while, you can have a solution where you take one of these little cards, put it in an adapter, and slide it right into your laptop. And again, you get power, you get fast interface, a lot of the things that you care about to be able to support this more intimate connection between radio and the host system. And then you move into things like tablets and embedded computer boards. I mentioned before the Jetson TK1, and there's another company out in California called Gateworks that specializes in making single board computers that have mini PCI Express slots. So we are trying to get these things to be as close to Lego bricks when we think about radios as possible, where we can put radios and hard drives and Wi-Fi cards and cell modems all into these platforms, taking advantage of the fact that they've got these mini PCIe slots, and use those to build real-world SDR solutions. You know, in a lot of cases what we find is the SDR is a piece of the equation, but almost always there needs to be extra stuff Frankensteined around it. So we're trying to look at ways to minimize the Frankensteining into these systems. So we've done work on a number of these systems, and we've talked to several customers here as well this week that are also playing with these more embedded platforms. You can do quite a bit once you start thinking about the problem as plugging cards into your host computing platform and having that be the final system. In the particular case of mini PCI Express, if you're not familiar with it, you get 3 watts. A little bit more than 3 watts in some cases. But the general thing is you got 3 watts to do everything you want to do. So that means you need your radio, you need your, if you want to have an FPGA on there, you got to have your FPGA, you need to have your PCI Express or USB interface all covered inside that power consumption. And if you go above it, the host system has the right to cut you off and say, sorry, I'm not going to give you power. So it really pushes the point of what can you do in a very limited power budget and still have a using the system. PCI Express, the spec gives you 1 lane of PCIe that can be up to Gen 2, which is a 5 gigabit a second theoretical throughput. You get a lot of data pumping through. Generally speaking, depending upon what you're looking to do, you can get upwards of 400 megabytes a second going over a single Gen 2 by 1 lane. And you also get USB 2.0. One of the things we found is we've done a lot of looking at mini PCI Express slots. Every vendor in the world is different. Some vendors are really gunning for the gusto. They put PCIe and they put USB in there, which is awesome. Some people just put PCIe and they say, forget about USB, who cares about that? And go, jerks. Other people put just USB and they forget about the PCI Express and go, okay, well, you got to live with what you can get over USB. Which isn't bad, it just kind of depends on the problem set we're looking at and what the host is doing. I mentioned antennas as well. Antennas are often pre-wired in these systems. The typical coverage you'll see for a given laptop or a tablet or other device that was meant to have a wireless card plugged into it, you'll usually see coverage from about 700 megahertz up to about a gigahertz. Covers a lot of the cellular bands. Picks up again someplace around 1600 meg to 2.2 gig, and then as you get into Wi-Fi, 2.4 and 5.0 and up to 5.9 gig. Gives you some general idea of what you're able to kind of expect with some of these host platforms. On Monday when they were doing the tutorial, there was a contingency of Sidekick developers here running their Sidekick laptops with the internal antennas. And I was personally surprised to see the FM receiver demo work fairly well, where you were able to pull out whatever station is not too far from here. Just remind everybody that even though your antenna is not rated A frequency, if you have a loud enough transmitter, you can still get something to go through it. So they were getting audio pulled out of their laptops just using the internal antenna, which is pretty cool. And last but not least, small. Small is good because it just lets you go into more places and work in more scenarios as long as you can figure out how to get the electrical and mechanical pieces worked out. So, I showed you some of the platforms that we've been doing integrations with. I may kind of skip past this. If you have interest in some of the other places where we've used Sidekick and some of the other platforms, some of the other commercial platforms where we've been able to use it, I'm happy to show you. We've got a few things that, a few other ones over where we're sitting. You can kind of go through. I do want to kind of give a quick shout out though to the two platforms I mentioned before, the GateWorks and antenna board that has a bunch of slots and kind of opens up interesting options, and the Jetson TK1. The reason I brought both of these up here again, the interesting thing with these GateWorks boards, if you're not familiar with them, they have a pretty capable processor behind them. It's a quad-core ARM Cortex-A9. So you have a pretty solid amount of CPU for an embedded platform, but you just have tons and tons of I/O options to be able to plop into these systems. So this is, I mentioned Lego bricks before, this is about as close as you can get in our book right now for being able to do interesting things at relatively low power. The thing that Jetson boards bring to the table is giving you a bunch of GPU cores to do something interesting with, right? So the TK1 has 192 cores inside of it, in addition to a pretty beefy ARM CPU, and magically they give you options for dropping in many PCI Express cards, which is cool. So this platform is actually not too far from what a lot of the newer generation tablets coming out of the market use as the reference design. It's not exactly the same, but it's not that far off of that. So, in the particular case where we're talking about our Sidekick card and kind of doing these integrations, this is the transition kind of over into the more GNU radio piece. So we provide blocks for being able to support GNU radio operation. There's a GR Sidekick block that we host up on GitHub that is continuing to get built out. For the longest time, it's been receive only. We've been getting more and more requests to add transmit support in there, which if you saw Megan earlier when she was here, she was spending some of the time this week to get some of that support added in. There are some other branches, if you look off of Master, that have some other features that we've been adding over time. So if you're using Sidekick and interested in that, poke around some of the different branches, of course. Until it gets over on Master, you may see some breakage, but it is definitely a continually improving space. So even with something like this, where we're able to run GR Sidekick in one of the typical waterfall clocks, right? We can suck in about 50 megahertz of spectrum. So a relatively large chunk, all over PCI Express, all with the Sidekick card embedded inside of an x86 laptop, all running GNU radio on the back. And we have some other customers that are doing, I'd say, more interesting things on the GNU radio side with this platform, including running GNU radio on some of the embedded boards that we talked about before. I mentioned the GateWorks board. I was talking with someone that we've worked with for a while, and they were mentioning some of the, they were hitting in the 20 megasample a second range of what they were able to actually get transferred up from the card over PCI Express into the CPU and into the radio land. So it gives you enough capability to do something interesting. And having 4 CPU cores makes a big difference for trying to handle some of the processing. Example benchmarks of the sorts of things you can expect to get here. We took 2 just because it gives a basis of of some, let's see if you're trying to wrap your head around kind of first order performance, what you can see. So the Dell E6440, which is a relatively current laptop you can buy from Dell, that has actually has 2 mini PCI Express slots inside of it. We've got some over where we're sitting if you want to check it out. It's cool to see what the final integration looks like. I've got a picture here, yeah. If you pop off the back of the laptop, this is kind of what it looks like. You've got 2 slots. There's a half-size card up at the top for Wi-Fi, and there's a full-size card, the rectangular area at the bottom where you can actually put a sidekick. But it's just kind of sitting there waiting to have an appropriate I/O peripheral plugged into it. So when we do benchmarking on this, we're generally seeing an order of about 200 megabytes a second moving between the card and the CPU. And the reason for the limitation there is on Sidekick in particular, we actually have a Gen 1.1 PCI Express, so it's not the full 5 gigabit a second. It's the 2.5 gigabit a second older version. That's actually because of that PGA that's on there. That's as fast as the FPGA will pump data between the two. So that's the idea that 200 megabyte per second limit equates to about 50 megasample a second if you're doing 16-bit I, 16-bit Q, sign extended samples. If you're willing to use the native 12-bit samples that are coming off the Sidekick and pack them, you can easily do 61.44 in either direction. The Sidekick uses the 9361 that a lot of people are familiar with in the previous analog devices presentation was referencing as well. And it's something like a laptop. If you plug a card in there, people often say, holy cow, it's got to get really hot. How do you deal with that? Laptop vendors think about these things, right? Tablet vendors think about these things of what do you need to do when you start putting a card in there. So they make sure there's some level of airflow, some level of management to ensure the cards don't get too hot. So even kind of cooking away, we're typically measuring in the mid 50 degrees C's for the actual on-card temperature for a Sidekick and a laptop. And similarly, if you start moving into these smaller embedded platforms, you can still get surprisingly capable performance out of it. No doubt, it's a fire hose, and the CPU, something like an ARM, will have trouble keeping up with it, but still, if you're hitting 50 megasamples a second on the receive side, and granted, this is outside of GNU Radio, this is sort of raw, what can you actually move over PCI Express into an embedded ARM and make work, you can still do quite a bit with it, and moving on to the pack space gets you even more performance. Looking at transmit and receive simultaneously, and specifically in the case of the embedded ARM, it actually drops the overall performance a bit more, so you have to make a few concessions if you're thinking about doing full duplex transceive, but still, non-trivial, interesting things can be done when you're looking at those sample rates. And something like a Sidekick running a Gateworks board, it's a little bit warmer, since it's sort of an open-ended question. Once you're plugging things, you're plugging things in here, you're making some assumption about, well, you can get some heat to the board itself, but almost always you have some sort of metal housing or some sort of thing over the board that gives you a little bit of benefit on the cooling side. I mentioned the antenna performance before. Antennas end up playing a pretty big deal in a lot of what we look at. This is that Dell laptop, one of the Dell laptops I mentioned before, and you can see there's lots of different antennas that are actually available to you. So the laptop manufacturers are often thinking about doing MIMO if you're going to do either MIMO or receive diversity or transmit diversity. So you open these things up and you see all kinds of antennas, and it takes a little bit of figuring to try to get your head wrapped around, well, what are they for, what bands do they support. We actually went through and did some measurements on a particular laptop to try to get a sense of what was actually supported here. So this is for the RF nerds in the world like myself, this is a return loss plot, which is kind of a good first order approximation of what you would expect to see in some level of performance out of the antenna for given bands. So this is by no means, this is not in a big anechoic chamber. This is us kind of doing, let's see how much energy gets reflected back from the antenna, which, like I said, is if you're an RF enthusiast, it is by no means a complete picture, but it is part of the equation when you're trying to assess an antenna. And you can see kind of what you would expect, right? In the 600 to 1.2 or 600 to 1 gig range, you can see where it starts to dip down, and that return loss, the more negative the number, the better. That means less energy is getting reflected back at you, and the energy is actually the antenna is doing kind of what it's supposed to do. So you see these little kind of dips down in the cellular bands, which is what you want to see for some of the antennas. You see more dipping in the 1.8 to 2 gig range, which is some of the European bands and Asian bands. You see more dipping at 2.4 gigahertz, and then you go up to the 5 gigahertz range, and you see even more. The interesting thing with this particular antenna, or this particular laptop, I mean, there's 5 antennas in there. So different antennas work at different bands, you gotta kind of figure out what those are. But it's not too hard to kind of reconcile that, and you actually get performance in some areas decently far away from the intended bands of operation. So it's a benefit on that case. You go through and you do a few measurements and you can kind of see what a reasonable potential range can be. So if we're doing ISM band operation, like if you want to work at 900 megahertz or 2.4 gig, all day long you're going to have reasonable performance with something like this. If you try to push it into the 433 ISM band, you'll get something out of it, but you'll get something out of the paperclip as well. So I mean, it's kind of a balancing act to see what kind of performance you actually need to get out of the system. The other thing we get asked a lot is when you do these really intimate connection between the radio and something like a laptop, you're like, well, don't you get blasted with spurs? And I'm here to tell you, laptops are nasty, nasty, nasty places. You have memory buses running fast, you have CPU core buses running fast, you have lots of things that can get in the way and make your RF activities kind of be less mushy than you, or more mushy than you would really like them to be. So this is, we went through and did some analysis on a particular laptop. So the test setup here is we've got a laptop with a sidekick embedded inside of it in the mini PCI Express slot. Inside of a big RF chamber, so in theory nothing is coming from the outside world, and no antenna attached. The red line at the bottom there is the no antenna attached line. It's kind of hard to see. The tick marks, the bottom corner is minus 130 dBm and minus 125, minus 120, minus 115, minus 110. So this is sort of open-ended, no antennas attached, just sitting there measuring what sort of extra RF artifacts would we expect to see inside of the laptop. And it is surprisingly good from what we can. We were surprised to see the level of performance we get when we have a Core i7 CPU drawing 35 plus watts a few inches away from this, and you got. If you remember that picture that I showed you before up here, you've got all the SO DIMMs in the memory literally about an inch and a half away from the radio side. So it is not a simple environment to be able to make work. Can you guess what the base CPU speed is here? You want to get the big spike right in the middle at 3 gigahertz is the CPU speed. So it's clipping up just above minus 110 dBm. So it kind of gives you some sense of what you would expect to see. But for a lot of applications, if you're looking at things below minus 100, minus 110, it's not an unreasonable option to be looking at. The blue line is a little bit different. The blue line is the same exact setup. Except we actually connected the antennas this time inside of the laptop. Because practically speaking, if you're going to do this kind of integration, that's what you're going to do. You're going to have the antennas plugged in. You're going to want to see what are you picking up with those. So everything comes up, which is expected, but still not all that unreasonable given the sort of integration that we're talking about here. The biggest spike, believe it or not, the one on the left side here is not even coming from inside the laptop. That's Verizon's 751 megahertz LTE channel that is booming loud. And even though we were inside an RF chamber, the attenuation still wasn't enough to keep that damn thing out of the signal. So that ends up being a very significant. So you can kind of erase that one. It was more an issue where we probably had some RF leak on in the test box where we were running some of these tests. But across the board, you're generally looking at below minus 100 dBm. So reasonable performance. The real takeaway here is just it's something you got to consider. You have to be thinking about when you're looking to do some of these sorts of integrations. Okay, so what needs to get better, right? It's a hard problem in general. The closer you're moving these radios, the more intimate you're connecting them to the host computing platform, you still have problems to deal with. The biggest single problem that we fight with is how do you get a good antenna in, and what do you do about filtering? The gentleman from DRS was talking earlier today, talking about pre-select filtering, right? Physics is still hard, it still kind of sucks. You still have to solve that problem in the general context of wanting to use these systems in places where you have lots of competing signals getting in the way. There's no doubt you can get away. It's a very viable solution for a lot of problem domains, but if you're looking for the absolute top-end performance, no questions asked, having some form of pre-select filter or antenna tuning makes a huge difference in being able to make these systems work. We're doing some work in that space as well to try to help augment what you can get out of some of these 0IF receivers and transmitters. If you're interested in that, come talk to me. We can give you a little bit more scoop. The second bullet there, the general idea of integrating more antennas. We want to see more antennas everywhere because more antennas and a way to get access to them makes our world happier. We can then get those antennas into our radios and do more interesting things with them. The third bullet, the mobile CPU space, and I'll say the corollary, sort of the integration of the more the graphics processors that are coming in, that is really starting to change the dynamic of what you're able, the amount of processing you're able to do on these smaller platforms. Some of the folks here are probably familiar with the work that Tom and other folks are doing with the Android version of New Radio, the GRN, or brand, I guess is the appropriate way to reference it. As that continues to extend and some of the working groups where we're looking at how do we accelerate computing by using some of these other blocks continue to extend, this is going to be a huge piece of making these systems with new radio and these very close connected radios work and do something interesting. So it's something that we're starting to take a more serious look at as well to see, well, how do we DMA directly from something like Sidekick over PCI Express right into the GPU and let the GPU have its way with it before we even bother giving it up to the CPU. So there's different paradigms that people are exploring to make some of these things work, and it's only going to be getting better. So the future. So what is coming down the pipe? So I mentioned Mini PCI Express has been around for a number of years at this point. If you track any of these small form factor computing card places, spaces, there's been a new standard that got ratified, I think at the end of 2013, and it started to make it into new computing devices. It's called M.2, or it's called NGFF, which stood for Next Generation Form Factors. Like, people come up with these acronyms. Anyway, M.2 is sort of the newer card form factor that's coming out and is out right now. So it is smaller than Mini PCI Express. Awesome. It's about 20% smaller in the configuration that I say is the most interesting. Although they have a number of different form factors. If you bought the more recent M-SATA drive, M.2 hard drive, you kind of see these longish, maybe an inch by about 6-inch little hard drive cards. That is using the M.2 form factor, but they have them for Wi-Fi, they have them for cellular cards, and in particular the cellular card form factor that has kind of predominantly come onto the space is this 30 millimeter by 42 millimeter by 2.3 millimeter thick card, which is not a lot of space. But it's still enough to do some pretty interesting things with. So we are going to be bringing a new version of Sidekick out towards the end of this year that we've been working on for a while that integrates everything we have in Sidekick, but updates the FPGA, brings it into a more capable FPGA. It'll be an RTX class FPGA, more of the RF being brought out on the 9361, a few other bells and whistles getting added to it. So you'll actually be able to do more signal processing on this sort of platforms, even though the overall size is starting to shrink down even more. The real win here is this is what's showing up in tablets and in computers, pretty much the predominant, interesting commercial places where we'd like to see these two worlds collide a little bit more. This is where it is all heading. We are going to stay in the Mini PCIe space for a while. The main reason is a lot of the embedded platforms. I mentioned these guys, these embedded computing platforms, the various ones that are out there. These guys don't really have a very compelling reason to go to M.2 at this point. There's a lot of Mini PCIe cards out there. They're not trying to shave every cubic millimeter that they can out of the system, whereas the tablet guys are just, ape shit about that stuff. They are trying to squeeze as much space as they can out of the system, so something like M.2 buys them a ton. So this has been under active development and will be coming out. If you're using Sidekick right now, the transition to the Sidekick M.2 is literally going to be seamless. You're just going to see more data going through because we're bumping up to Gen 2 PCIe, so you'll get the full 5 gigabit a second coming over the pipe and more FPGA to do interesting things with it. And last but not least, this RFIC world keeps improving. Vendors are really good at competing and making more radio chips, which is awesome because folks like ourselves who build radio platforms can take advantage of that and get them into new systems and even very, very small systems be able to do interesting things with them. So when we talk about these improvements, we're talking about more bandwidth, we're talking about better dynamic range, better linearity, lots of interesting things coming down the pipe. So yeah, keep an eye out for more announcements with what's coming there. So yeah, so in conclusion, mobile computing platforms are smaller and more capable. We are trying our damnedest to get radios as tightly coupled into that space as we can. Generally being small is good, being low power is good. It's true it will not solve every radio problem out there, We had a customer come to us and say, hey, I'm using this Rode Schwartz radio that's, pretty big and it's, kind of expensive, and are you guys better than that? We're like, man, Rode Schwartz knows how to make radios, right? It's just a matter of we're interested in a different part of the pie, right? This is a 80% solution for an awful lot of problems out there. It is not going to give you the instrument quality performance that in some applications you need, but there's a lot of places where it is a very, very, very sufficient solution, especially when you can kind of think about moving into this mobile space in the Czech Republic. So smaller platforms, mini PCIe and M.2, bringing new radio into the mix and have that intersection, super interesting to us. Love to talk to you if this is also something that's interesting to you. We, the next 6 to 9 months, have lots of things in store, so we are excited about it, and I'll do the same plug that other folks have done. If you dig this stuff, we are hiring as well. We have a team of 24. We'd love to build more things and make things out there. So that's my talk. Thank you very much.
All right, do you have any questions for John? Yes.
Hey John, I was just wondering, do the Sidekick cards, do those support like 10 meg 1 PPS timing references?
Yeah, so Sidekick lets you bring in an external PPS, and it goes right into the FPGA, and you can get timestamps. You can query the last timestamp of PPS and use that as a synchronization signal. And you can bring in an external reference clock to the system if you want to phase lock multiple parts. We've done configurations for customers where we'll put 4 Sidekicks on one of these GateWorks boards. We actually have another product that is, this is Telecom, mostly engineers at our company. We have another product we've been shipping that's still not up on our website called PlaceKick. PlaceKick is a mini PCIe card with a GPS receiver and clock distribution, so you can bring in external 10 meg and PPS or get GPS, and it'll distribute it times 4 of the 4 Sidekick cards. So you can effectively either get 4 or 8 receivers all running off of common reference clock. So there are options for doing that, yes. They're really small connectors though. They're WFL. If you haven't seen WFL, man, people are crazy. They're really small. They're really small.
All right, any more questions? Oh, all right, thank you, John.
Thanks.